Okay, so now let's talk about another reaction, which is the hydrogenation of alkynes, or a reduction of alkynes. Just like with our alkenes, we can do a catalytic hydrogenation of an alkyne, which is taking hydrogen gas over one of these solid surface catalysts, so either palladium, platinum, or nickel. And what you're going to get is a hydrogenation or reduction of these double bonds in the presence of hydrogen gas and palladium. This catalytic hydrogenation, you're actually going to get an alkane, not an alkene. Okay, so it's going to be a full hydrogenation or a full reduction of that triple bond. Of course, we get that syn addition originally to our pi bond. The problem is by design of these experiments, because you've just mixed this in with this surface catalyst, you can't stop there. There's always going to be another round of reduction or addition of the hydrogens that's going to completely reduce that double bond to an alkane. Okay, so this would be hydrogenation is the full all the way to an alkane. But what if we want to stop it at an alkene, just a one-step reduction? For that, we can use special catalysts. So the first one is another surface catalyst. It's called a poisoned catalyst, which is basically means it doesn't work all that great. The most popular one, and the one that you're going to see over and over again that I use, is this dude Lindlar's. So Lindlar's catalyst will stop at an alkene. And again, it's a surface catalyst. So just like before, we have a syn addition to this triple bond. And so we will selectively produce the cis or Z stereoisomer. Okay, so these are stereospecific reductions that stop at that alkene. Okay, so now this is what Lindlar's catalyst looks like. I don't even know that. Bottom line is recognize that name, Lindlar, and know that that's one of these poison catalysts, solid surface catalysts, meaning it will stop at the alkene. And again, important because it's a surface catalyst, it's a syn addition. So then obviously the next, well, I guess just to sort of illustrate this in terms of our free energy diagrams here, even when we were talking with alkenes, we had noted that we have to have a catalyst, because even if we started with an alkene, that barrier without a catalyst is really, really high, right? So we used a catalyst to decrease that activation energy. So this is an example of what it would look like with one of our poison catalysts or with Lindlar. That first step, starting with an alkene, is indeed that activation energy has been decreased, so that can proceed. But the whole shtick about the Lindlars is that it does not decrease the height of that second activation barrier very much, at least, to the point where you don't have any formation of the alkane, right? Again, the whole idea of Lindlar is we're able to stop at that alkene. Again, important, it's a cis. So then the next question is, well, what if I want to form the trans stereoisomer? We have another method of doing this, and this is using kind of an odd combination here, sodium metal in ammonia. And actually these take place at like -78 degrees Celsius. So really, really cold ammonia and sodium. Sodium is incredibly reactive. It does not, so this is actually sodium, not the sodium cation, but we're really talking about sodium metal with its one electron. If we remember back to general chemistry, those first column elements, sodium, potassium, they really, really want to get rid of that electron, right? So that's, if we didn't do this under really, really cold conditions, it would be a little bit explosive. So that's part of the reason why we're going to do this in liquid ammonia. Okay. So the mechanism here is not actually one that I expect you guys to have memorized, but it is nice to just see. What we have is the sodium is going to be donating an electron. And one of the things I want to note here are these arrows. They're not double arrows, they're single-headed arrows, which means they're showing the migration of just one electron, not two. So what happens is sodium is going to go, again, it really wants to get rid of that electron, right? So it's going to donate that electron to this triple bond, and that's going to cause a heterolytic cleavage of that triple bond. So again, we have these single-headed arrows, which means that from this pi bond, one electron's jumping onto one carbon and the other one onto the other. So what this produces are these two electron clouds. One of them is a full paired electron cloud, so it's got this negative charge, and that's going to reach over and steal a hydrogen from the ammonia. Okay, so that's going to be, it's going to protonate that alkene. And then you're going to have another round of reaction where now we have this only singly occupied electron orbital. Again, sodium is going to be involved, and it's going to go ahead and donate its electrons to pair that up. And then another second round of proton transfer where that electron cloud is going to reach over and steal a proton from ammonia. Okay. Being able to draw this reaction mechanism from memory isn't the most important thing. What I do want you to know is why this produces the trans isomer. And it has to do with that very first step, right? Where we form these two electron clouds, one with a pair and one with a single electron. We call this a radical. The bottom line is that it is way lower energy for these two electron clouds to be on opposite sides of the double bond than it is to be right next to each other. This is much higher energy because you have repulsion that takes place between these two electron clouds, right? So this would be an anti-addition or produce the trans isomer. Okay, so now let's just summarize real quick. Note the similarity here, here, and here. Anytime we use hydrogen gas and one of those really good surface catalysts, again, palladium, platinum, or nickel, we're going to go all the way to that alkane, okay? In terms of mechanism, actually I had colors for these, what were they? So mechanism, you don't have to know it for these solid surface. Regioselectivity, there is no regioselectivity because you're adding hydrogens to both positions, right? So there's not sort of like, which carbon do I add my hydrogen to? You're adding hydrogens to both. And then in terms of stereoselectivity for these H2 palladium reactions, the only ones, you do have to know that it's a syn addition, but that's actually only important if you're starting with an alkene. If you're starting with an alkyne, you will end up adding 2 hydrogens to both carbons, which means that you haven't created any stereocenters. Now let's talk about the Lindlar's catalyst one. So again, mechanism. So now we're talking about Lindlar's here. Mechanism. Again, you don't need to know. Is there regioselectivity? Again, not a problem because you're adding hydrogens to both carbons. The big thing here is the stereoselectivity and the fact that this is going to be a syn addition, right? So that is the most important distinction when we're talking about Lindlar's. Yes, we stop at an alkene, but not only do we stop at an alkene, it's a syn addition, so we create that cis alkene. And this is in contrast to where we're using that sodium. Again, mechanism, no. Regio, no. It's only the stereoselectivity that we need to know about, and that this is an anti-addition, right? So we're going to be adding hydrogens to either side. Okay, so that's the big difference between especially Lindlar's catalyst and this sodium and ammonia. One is a way to generate a cis alkene from an alkyne. The other one is a way to generate a trans alkene from an alkyne.